Hi everyone, so today we're going to look at exponential growth and decay through real life or word problems that are supposed to represent real life. Some common examples of exponential growth include population. Population grows exponentially. You guys have seen firsthand how this virus has grown exponentially. So you'll see, and bacteria grows in the same way. So you'll see problems that are centered around bacteria growth, population growth, as those are typical examples of exponential growth, right? So as the x value increases by a small amount, the y value increases dramatically. That's the idea. So we're going to still be using this formula that you see down here, y equals a times b to the x. And for part A, you'll notice for each problem it asks you to write the equation. When you're asked to write the equation, you're going to be writing it in terms of x and y, just in general. Okay, this is in terms of x and y. And then you'll be asked to find a specific value for a specific time period. So in example 1, the population of a city increases 2% each year. The population is now 30,000. So I'm going to start with the population is now 30,000. This is your initial value. Initial value, if you think back to linear functions, represents your y-intercept. So in an exponential growth problem, that's your a value. Your initial value is your a. So I'm going to write y equals 30,000 is going to be my a value. I'm going to write the formula above. And then I'm going to think about b. Yesterday I briefly mentioned b. B is 1 plus the growth rate. B equals 1 plus the growth rate. I'll write it below afterwards. So imagine however many people you have to start with, right? I'm going to represent that as a circle. That's considered to be 100%. Plus, there's a rate of 2% each year of growth. So what we do is we express these as decimals. So 100% is 1, right? I move the decimal back 2 places, and 2% is 0.02. And I add them together to say 1.02, meaning that 1, whatever I started with, 100% plus 2% each year. And this is going to be raised to the x power, where x represents the number of years. This is my general equation for this situation in terms of x and y. And then I'm asked in part B to find the population in 10 years. So that means that my x value is 10. I'm going to plug it into my equation. Y equals 30,000 times 1.02 to the 10th power. Okay. So in your calculator, if you're using a graphing calculator, you're going to use this caret button that I just drew over here. This caret button, which indicates to the power of. So like to do 30,000 times 1.02 to the 10th power, I would type in 30,000. I would type in times 1.02. Then I would use the caret button to the power of, and then type in 10. Now, if you're not on your graphing calculator, if you're on a scientific calculator, you might have that same button, or you may have a key that looks like this, x to the y power, or some other version of that, where you would use it in the same way. So you should get, if you type in 30,000 times 1.02 to the 10th power, you should get 36,569.8, which to round to the nearest whole is going to be 36,570. Okay, so you can pause the video and just make sure that you know how to use your calculator to arrive at that answer. So in general, we have this formula, y equals a times b to the x, which we're still using. I'm just going to erase that box. A represents your initial value. B is 1 plus the growth rate. But remember that these have to be expressed as a decimal. And x is the time period that you're, the number of years usually. Okay, so in the second example, they talk about healthcare costs. In 1985, the daily cost of patient care in community hospitals in the U.S., since 1985, it's increased about 1.8% each year. In 1985, the costs were an average of $460 per day. So first we're writing an equation in terms of x and y again. Maybe take a minute to pause the video and write that equation. So you should have y equals the initial cost of healthcare is $460 per day. Everything is per day here, so I don't need to show the per day part. And then for my b value, I'm going to take 1.8%. I'm just going off to the side. To express it as a decimal, I divide by 100, so it becomes 0.018, and I add 1 to that, right? So that represents whatever it started at, 100% plus 0.018 or 1.8%, and this is going to be to the x power. Okay, and then find the cost of hospital care in 2020, so that's 35 years later. So I'm going to now use 35 as my x value. So 460 times 1.018 to the 35th power. If you plug that into your calculator, you'll have 858.875. So it's just the nearest cent, that's the nearest hundredth, so $858, and it's 87.5, so 88 cents. Okay. In the next section, we're looking at equations that have already been set up for us and analyzing what the different parts of the equation mean. So for part A, what's the initial value? Your initial value is always going to be the A value, so this is 300. What is the growth rate? Remember, the B value is 1 plus the growth rate, so you have to take that apart a little bit. The growth rate here would be 3%, so you're looking at the 0.03, which represents 3% growth each time period. Okay, you can pause the video and try example 4. In example 4, the initial value is 5,000. And the growth rate, be careful here, 2 is really 1 plus a 1, right? So the growth rate is 100%. And that makes sense because if you think about what we graphed yesterday, when the B value was 2, the Y values kept doubling, right? So when something is doubling, it's increasing by 100%. Okay, so think about when something is tripling, what's my B value going to be? If I have a tripling, then my B value is going to be 3. It's an increase of 200%. So if my, just as another like aside, if my B value is 3, then this is tripling, right? But this represents what percent growth? It's a 200% growth. Okay, because it's increasing by 200% on its original amount. Okay, exponential decay. So there are rare situations with population where it decays. So usually population grows, but if there's like some sort of natural disaster in an area or economic disaster, people will leave and the population might decrease exponentially. So those are some examples with population. And then another very common example of exponential decay is if you want to know how old like a fossil is, they use radioactive decay. So the amount of radioactive substance decreases usually by exponentially. So when they detect how much radioactive material is, or not radioactive, sorry, carbon dating they use. So carbon, the amount of carbon in that living thing decreases exponentially. And so they measure how much carbon is remaining, and they kind of like then use exponential functions to work their way back to figure out how old that specimen was or is. And then there's radioactive, elements decay also exponentially. Different example that I confused together. So anyways, you'll see some examples related to those. Let me pause the video right now, and I'm going to, because otherwise it's too long and it won't post, and I'll move on to the next one.